So, everybody, let's look into limitations of perceptrons. Well, as we have said, perceptrons are mathematical functions. They map from r to the n plus 1 to r, and they have a specific form, namely, it's a nonlinear function called sigma put on top of a linear product that multiplies the input x with a weight vector w. And the original perceptron learning algorithm, as defined by McCulloch and Pitts, used that step function, also called threshold function, that takes exactly two values, value 0, value 1. And the value 0 is taken on if the input argument set is negative, and if it's the input argument is greater or equal than 0, then the value of the step function is 1. So, and these two values can also be seen as two labels. So it gives a label of 0 or it gives a label of 1, depending on whether the argument is smaller than 0 or greater or equal than 0. Now, what is a hyperplane? A hyperplane, HW for a given point W, is the set of all points x1 to xn such that x tilde, which puts an additional 1 into x, multiplied by w, like in a dot product, yields the value 0. So the set of all points in r to the n that has the property that these points multiplied by w yield the value 0 are called a hyperplane. And in two-dimensional space, we can just rewrite it ourselves. We just have two values, x1 and x2. So the equation becomes x1 times w1 plus x2 times w2 plus w3, because there's an additional 1 in here, which we multiply with w3, equals 0. And this we can rewrite into equivalent form, where we put x2 on the left side and x1 on the right side, and you can easily recognize that this is the equation of a straight line, because a straight line has the equation y equals az plus b, and this is exactly this form. So this is basically a hyperplane in two-dimensional space. Is just a straight line, right? And in three-dimensional space, it would be a real plane. And in 4, 5, and 6, and 10-dimensional space, we call that a hyperplane. So this is just a generalized straight line, so to speak. And this hyperplane is interesting in connection with the perceptron, because you see here that the perceptron with this standard step activation function also makes a decision based on a hyperplane. Why does it? Because if this set, so this set is x times w, right? This is exactly this term here. So if we're on that hyperplane, we can consider the network to be kind of undecided. So on the hyperplane, it gives exactly the value, it gives the value 1, but it's kind of undecided, because if the input argument would be a little bit decreased, then it would give the value 0 on, and on the hyperplane it switches the decision, and to the right of the hyperplane or to the other side of the hyperplane it always gives a 1, and to the left of the hyperplane, to one side of the hyperplane, it gives the value 0, to the other side of the hyperplane it gives the value 1. So this is the connection between hyperplanes and this threshold activation function. Now, what is the decision surface of any machine learning classifier? So as we will see in lecture 2, there are different machine learning classifiers, and they have decision surfaces. What do these decision surfaces mean? Well, machine learning classifiers, it gives out typically, like in a standard setting, it gives out classes. So it says this point is a dog, this point is a cat, this point is an elephant. So it labels objects, right? And the decision surface is a boundary region where on one side of the boundary region a specific label is given out, and on the other side of the the boundary region, another label is given out. So in this example, you see pluses and minuses. So this classifier would label pluses on this side of the boundary region, and it would label minuses on the other side of the region. And as we have seen, the perceptron has exactly as a decision surface this straight line. So whenever it's on the straight line, it would give pluses, and everything to the right also pluses, and everything on the other side it would give minuses. So the decision surface of a perceptron is a linear line, is a hyperplane, so to speak. And then there's a theorem that says, and this goes back to Frank Rosenblatt, if the data is linearly separable, then the original perceptron learning algorithm converges after a finite amount of time and classifies all training data correctly. So what is the original perceptron learning algorithm? Well, that's a variant of the algorithm that we've seen before. So before we derived some algorithm how to train the perceptron model, and the original one is similar to that. It's a little bit different, but the differences don't matter now for our purposes. Okay, so this means if data is linearly separable, then the perceptron learning algorithm can really classify that data correctly, and the classification is given by 0, 1, right? It's this output of the nonlinearity 0, 1. Now, what does it mean for data to be linearly separable? Well, here's the formal definition. Well, whether two sets are linearly separable. And this formal definition precisely says, can we put a hyperplane between these two sets? Yeah? Can we put a hyperplane between these two sets such that all points that belong to one of the sets are on one side of the hyperplane, and all of the other points that belong to the other set are on the other side of the hyperplane, right? So that means for two sets to be linearly separable. So let's make an example. Well, what is the OR problem? The OR problem, you can model the OR problem in terms of sets. So the OR problem could be considered as consisting of these two sets, x0 and x1. So why these two sets? Well, because the OR problem assigns the value 1 to all the points in here, and it assigns the value 0 to this point here. And now we show that the OR problem is linearly separable. How would we have to choose our W? So basically, a linearly separable means you have to find a hyperplane. You have to find a hyperplane such that this hyperplane separates these two sets. Well, and we can set our hyperplane to use this weight vector W here. So recall the definition of a hyperplane had that this hyperplane had a parameter vector W which characterized the hyperplane. So that basically says, where does the hyperplane go through this W? So now we have to find such a hyperplane, and we choose it to be parameterized by the vector 1, 1, minus 0.5. Let's do a quick check that this is actually true. So does it really follow that all the points in Zx0 are on one side and all the points x1 are on the other side? So we do the calculation. So we multiply this point here and we add a 1, because we have to add the 1 in the last component. So we multiply this point with the weight, and this gives 0 times 1 is 0, 1 times 1 is 1, so that gives a 1, and 1 times minus 0.5 gives 0.5. So overall 0.5 comes out. For this value here also 0.5 comes out. For this value here we have 1, 2, 1.5. So all these three terms have positive numbers. So this means that they are on the same side of the hyperplane. And this value here has 0 times 1 is 0, 0 times 1 is 0, and 1 times minus 0.5 is negative 0.5. So this point is on the other side of the hyperplane. So indeed, the OR problem is linearly separable. Okay, and we know that now from our theorem, due to Frank Rosenblatt, that the OR problem, that the perceptron learning algorithm can solve the OR